All right, good morning, everybody. Welcome to Mrs. Rivera's Khan Academy. This is going to be super awkward. I am not comfortable talking into my computer screen to give you guys these lecture notes. So I'm sorry if I talk too much or too long or too short, and my handwriting is still not great on this tablet, and I promise that I will get better. Okay, so enough of that. Here we go. We're going to take a look at chapter 19, which is thermodynamics. Reminder that this is not going to be on this year's AP exam. They cut this out because of your shortened year. I think we should still look at it because it helps tie together this concept of enthalpy and entropy into this new concept called free energy, which helps us determine whether reactions are spontaneous or not. So I think it's really valuable to talk about. You're certainly going to need it in college chem. So we're going to do like a little abbreviated week-long thermo, investigation. So anyway, we studied in, I want you guys to remember that we studied thermochemistry back in chapter 5, right? And thermochemistry was when we were doing like Q equals MC delta T, when we were looking at temperature changes involved in reactions and calculating how much heat was being produced or absorbed by that reaction. And we turned that into a delta H by dividing the amount of heat produced by the moles of the limiting reactant in that reaction. Because remember, if you react more stuff, you're going to get more heat, but we want the heat of the reaction to be a standard value. And I also want you guys to remember that if you have a positive delta H, we would call that an endothermic reaction, and that reaction absorbed heat. And this is less favorable in terms of spontaneity. Like, if a reaction requires an input of heat in order to occur, it's less likely to occur. And if we have a negative delta H, we would call that an exothermic reaction, where heat was released. And this would be considered favorable. Now, we've seen lots of reactions that happen spontaneously that were exothermic, but we've also seen lots of reactions that happen spontaneously that are endothermic. And the question that we have to ask ourselves is like, if that is less favorable in terms of enthalpy, why is it that that reaction is spontaneous? So we're wondering, how is it? This doesn't do the dots very well. I have to there we go. I have to circle them in there. How is it that an endothermic reaction can be spontaneous? Great question, you guys. Let's explore that. We've talked about why that is, right? I've hinted at it over and over again, that it turns out that spontaneity of a reaction does not just depend on enthalpy, delta H. It also depends on something else called entropy, delta S, or the disorder involved in a reaction. Now, we're not going to have this conversation just yet. First, I want to talk a little bit more about what it means to be spontaneous. Okay. So, a spontaneous process is one that proceeds without any intervention, like it just happens on its own. Meaning like you don't have to do anything to get that reaction to occur. So for example, like if you leave an iron nail, out over time, it's going to rust, right? So like that reaction is happening spontaneously. That study of the spontaneity of reactions is, in fact, what thermodynamics is looking at, right? So I guess I didn't actually define the difference between thermochemistry and thermodynamics. Thermochemistry is just looking at heat. Thermodynamics is looking at all energy involved in reactions. The energy associated with the heat of the reaction and the energy associated with the disorder of the reaction, or the entropy, if you will. So let's just remind ourselves what we're talking about when we're talking about energy. There's a couple of laws of thermodynamics. The first law of thermodynamics is that energy is conserved. And you guys remember, hopefully, that, oh my God, I pushed the wrong button, sorry. That the change in energy of a reaction is equal to the amount of heat transferred plus the amount of work that is being done. So that's your first law, is that like whatever total amount of energy transfer is taking place is a combination of heat and work. Just a little review about heat and work. Negative Q means heat was released by the system. A positive Q would mean that heat was absorbed by the system. A negative W would mean that there was work being done by the system on the surroundings. Like the expansion of gases, you know, so like if you have this piston here and this reaction is taking place and it causes that piston to move up against the atmospheric pressure, this system, this reaction was doing work, so work done by the system on the surroundings, on the atmosphere. And the reverse case, if that piston were to be pushed down by the atmosphere, by the reaction, that would be a positive W. That would be work done on the system. Okay, so that's just a little review of internal energy and the first law of thermodynamics, because we are going to address the second and third laws, which have to do less with heat and more with entropy. So, okay, so definition of a spontaneous process is a process that will proceed without any intervention. Like this just happens on its own. A reaction that is spontaneous in the forward direction will be not spontaneous in the reverse direction. So a reaction that is spontaneous, I'm just going to abbreviate here, in the forward direction is not spontaneous in the reverse. I think that's pretty obvious. And the other thing that I wanted you to recognize about the spontaneity of the reaction is that it says nothing about rate. Okay, it says nothing. It is not related to rate at all. About rate of reaction. So just because a reaction is spontaneous does not mean that it's fast, right? So rates are totally separate from spontaneity. However, spontaneity will relate to equilibrium, okay, but it's not going to relate to rate. And I'm just checking my notes to see if there's anything else that I wanted to talk about with regard to spontaneity. I think that was it. Okay. So let's move on. Again, this is certainly an abbreviated lecture. So like when you guys go ahead and take a look at the text, there's going to be some things that I'm not covering in this lecture that get covered in the textbook. In fact, when you guys go to college, if any of you go on to become, civil or mechanical, specifically mechanical engineers, you're going to take like 2 full semesters of thermodynamics because this is how engines work. This is, anything involved with energy transfer, electrical engineering, aerospace, all of those types of engineering are really going to be heavy on thermo. So we're just going over it really generally, so don't get overwhelmed when you see some equations in the book that I'm not referring to here. Okay, so anyway, now's the time where I want to talk more specifically about entropy, because what we're trying to do with this whole unit is look at how enthalpy, delta H, relates to entropy, delta S, to determine whether a reaction is going to be spontaneous or not. So let's take a look at this factor. Entropy, S, is a measure of the disorder of the system. Now, by disorder, I mean randomness. By disorder, I mean messiness, right? Like I've done this example before in class where like I totally trash my front lab bench, right? I spread all the papers all around the lab bench and it's like when the papers are spread out all across the lab bench, there's way more randomness. There's way more possible positions for all of those pieces of paper. One piece of paper could be next to, 400 other pieces of paper. So that's what I mean by degrees of disorder or messiness or randomness. We'll talk more about like what that means and looks like at a molecular level here in a little bit. Okay, so we'll also talk about how we measure this. But before we talk about that, it's important to recognize that entropy is a state function, just like enthalpy was. Now, a state function, if you recall, only depends on the initial and final states of the system. Like it doesn't matter what path you take to get there. For example, the difference in altitude between Boston and Denver is like a mile, right? It doesn't matter like how I get from Boston to Denver, whether I fly, whether I drive, whether I go all the way down to Texas first and then shoot back up to Colorado. It doesn't matter how I get there, there's going to be a mile-high difference in elevation. So elevation would be a state function. But distance traveled to get from Boston to Denver would not be a state function, right? Like I could actually drive down to Texas and then shoot up north to Colorado and travel way more miles than I needed to. So because entropy is a state function, we can actually just calculate the change in entropy or the change in disorder of a reaction or a system by taking the entropy of the final states minus the entropy of the initial states. So like how disordered does the reaction end up versus how disordered the reaction was initially will give me my delta S of the reaction. Okay. Now, the second law of thermodynamics states that the entropy of the universe increases in all spontaneous processes. In other words, if you have a positive delta S, your system or your reaction is becoming more disordered or messy. And this is favorable in terms of spontaneity. Now, again, a reaction can be spontaneous even if it doesn't increase disorder. Okay, so because remember, whether or not a reaction is spontaneous is going to depend not just on entropy, but also on enthalpy. Okay, but in terms of favorability for entropy, for a reaction to become more disordered, that's favorable, right? Because the universe, according to our second law, right, is tending towards disorder. If you have a negative delta S, the system is becoming less disordered. I have a hard time with like less disordered, so I like to call that more ordered. I don't know. It just like makes more sense in my head. Ordered. There we go. And this is not favorable. Now, again, a reaction can be spontaneous, even if it's becoming more ordered. And we'll talk about that relationship with entropy and enthalpy later. Okay, so it's not favorable, or less favorable, we should say. Okay. I would say any questions, but you guys aren't here, and this is very lonely, and I feel like a crazy person just talking into my computer screen. We'll get through this. Okay, so what does disorder look like at the molecular level, right? Like what does it mean for molecules or atoms to be disordered? Okay. We as chemists call the possible positions or arrangements that atoms and molecules in a sample can have, we call these microstates. And hopefully you guys watched that little intro video that maybe confused you, but I think this conversation will help clear that up. So these possible arrangements and positions and distributions of kinetic energy amongst atoms in a sample are called microstates. And the more microstates you have, the more disorder you have. Okay, so if you have an increase in your number of microstates, you have an increase in entropy. Why is my screen being like that? Stop it. Increase in entropy. A positive delta S. Okay? What did I want to say? Oh, I remember. Okay, when we talk about kinetic energy of atoms and molecules and units, samples of substances, there are 3 different types of molecular motion that we could be referring to here. And I just wanted to introduce those 3 different types of motion. Well, 1, because they're interesting, and 2, because we don't often think about, like, I know we always talk about molecules in motion, but what are we really talking about here? We certainly talk about how fast they move, but there's also like different types of movement. So the 3 different types of movement, the first one is called translational. Oh my, I think I need to hold my pen a little differently. I keep hitting this button that I don't want to hit. Okay, so translational motion would be sort of like your directional motion of molecules. Like if you have one molecule that's starting off here and then it moves across space and time to over here, that's what we consider to be translational movement, or like directional movement, you know, directional movement. So like, for example, you know, you can smell my candles that are burning in my room, like all the way down the hallway, because those gas molecules have like moved from my room, like down the hallway. They have this directional motion. There's also something called vibrational movement. And that's just like it sounds, right? It's talking about how those molecules move towards and away from each other, right? So like if I have a sample of a solid and these particles are pretty close together and they are vibrating, or they have their own internal kinetic energy, so they're moving back and forth with relation to each other. So we're not talking about how far did this molecule move across the room, especially not in a solid state, right? It's not moving across the room, but they are vibrating next to one another. So that's vibrational motion. So with relation to other particles. And then finally is rotational. And that's like how a molecule rotates about its own axis, right? So like if I have a water molecule here, this water molecule could move directionally, like it could, like, you know, as water vapor, it could like move across, you know, the room. It also, if you're talking about like ice, you could really have a good example of its vibrational motion, as those particles still have kinetic energy. They're not at absolute zero. So they are vibrating and moving next to one another. But if you think about something in like the liquid state or in the gaseous state, like this molecule itself just turns around on its own axis. Like it could be oriented like that, but then a few minutes later, its kinetic energy could have it, you know, oriented like so in space and time. So the rotational movement as well. That's actually not super important for anything, but I just think it's interesting. I like those 3 vocabulary words. Anyway, so I guess I should write something here. Movement about its axis. Okie dokie. So what will result in an increase in microstates and thus an increase in entropy? So there are a couple of things that are going to cause something to have just more internal disorder and microstates for a sample, okay? So let's think about what some of those things are. Certainly, a solid becoming a liquid, a solid becoming a gas, a solid being dissolved in solution, that's going to increase entropy, okay? Because when you're in a solid state, you're locked into this very orderly arrangement, and like this particular atom up here, this guy, why isn't it writing? Oh, making it big and dark. This guy can only be next to this guy and that guy, right? Like there's no other possible position for him to be in. But if we were to overcome those intermolecular forces and spread, I'm like using hand and arm motions that you guys can't see, spread those molecules out into a gaseous state, now this particle could be next to this particle because they can all move around. Okay, so solids becoming liquids, becoming gases, becoming aqueous, are all going to increase entropy. Liquids, mixing a liquid with another liquid to become an aqueous solution. A liquid becoming a gas will also increase entropy. The other direction would not, right? Like a gas becoming a liquid or a liquid becoming a solid. Those would be more ordered, and the reverse direction is less ordered or more messy. Now, notice, I am not going to say that a gas going into solution increases entropy. It does not. A gas going into solution would be more ordered because gas molecules are really spread apart and they can have many more microstates in the gaseous state than they could in the aqueous state. So you can see I said solid to aqueous increases entropy, liquid to aqueous increases entropy, but gas to aqueous does not. Okay. What else? Oh, I know. If we have a reaction that goes from less moles of gas to producing more moles of gas, that will increase entropy for sure, because now you've got more particles, more possible positions and arrangements for them to be in. What else will increase entropy? Let's just talk about some of the other factors. Like, obviously, we were talking about, the more motion that they have, the messier they are. So increases in temperature or increasing in kinetic energy will increase the disorder of a system. If you increase the volume of the container, now they've got more possible places to be in. If we're talking about a gas. What else? What else? Why do I feel like I'm forgetting? Hang on, I'm just going to look back at my book so I don't forget. Oh, you guys, I haven't finished my coffee yet. Okay. Volume, temperature. Oh, duh. Like if we're talking about two different substances, right? So for example, if we're talking about like CH4 versus CCl4, similar tetrahedral shaped molecules, like which one of these is going to just have more internal entropy or possible positions or microstates or disorder? It's going to be this guy. When you have an increase in molar mass, you've got an increase in the number of electrons and thus an increase in the possible positions of all of those electrons, right? So of course, bonds are like areas of probability where electrons can exist. And so if you've got an increase in that number, you've got an increase in the number of possible places for those electrons to be. So this also, when you have an increase in molar mass and an increase in the number of electrons, you're going to have an increase in disorder or microstates. And, if you're talking about a sample, simply an increase in the number of particles in that sample, right? So if you have a sample that's, 5 grams versus a sample that's 10 grams, if you've got many more particles in the heavier sample, you're going to have an increase in the disorder or the messiness of that system. And now I think I've talked about all of the things that can possibly increase entropy. So maybe it's time for you to practice. Is that what I said I was going to do next? Yes. Okay. So I think what you guys should do now is I would like you to maybe pause the video and take a look at each one of these examples, A through D, and tell me whether or not you think that entropy is increasing or decreasing for this process. Tell me if it's going to be a positive delta S or a negative delta S. Let's go ahead and pause the video now. And welcome back. Okay, so when we have water in the liquid state going to water in the gaseous state, that is going to be an increase in entropy, positive delta S. When we have dissolved ions in solution precipitating out as a solid, that would become more ordered or less entropy, negative delta S. Here we have a solid and a gas becoming just a solid. This is the rusting I was referring to earlier. Oh, I'm so glad I picked this example. Sorry, let me answer one thing at a time. Okay, so a solid and a gas becoming a solid, that is becoming more ordered or less disordered, negative delta S, less entropy. However, I was just talking about how this reaction is spontaneous. And you're like, well, wait a second, Mrs. Rivera, that's not favorable, that this has a negative delta S. So how is it that if it's becoming more ordered, it happens spontaneously? It's because it has to do with enthalpy and temperature too. So we'll talk about that later. And here I can see everything's in the gaseous state, so it's not about changes in state. So if I've got 2 moles of gas here on the left, and I have 2 moles of gas here on the right, the delta S will be close to 0. There won't be a big change here in entropy. Now, of course, we could be looking at molar masses. Certainly here we have 2 different substances, and here we only have 1 substance. So there could potentially, if we looked more closely at all of the factors involved, there could be a small change in delta S, but it's really going to be governed mostly by the fact that we've got same moles of gas on the left as we have on the right. So you're not going to get a big change in entropy. So you could say that the entropy would be close to 0 in that case. Okay. Now, what are these like actual values here, right? Like these, when I keep talking about these qualitatively, these S's can actually be measured values. And we call those measured values standard molar entropies, okay? Just like we have standard heats of formation for substances, we have standard molar entropies, like values that we can actually measure the degree of randomness of a particular type of substance, depending on its state of matter, depending on its molar mass. So this is my symbol for standard molar enthalpy. That little 0 guy up there is a not symbol, which is just meaning under standard conditions. And standard conditions would be 25 degrees Celsius, which is our room temperature, 298 Kelvin, and 1 atmosphere of pressure. So all of these values you can actually look up in the back of the book. They are in Appendix C. And if you guys recall, when we were looking up heats of formation, for standard heats of formation for substances, that's like the amount of heat released or absorbed when a substance is formed. Remember, this value is equal to 0 for elements in their standard states, right? They all got formed during the Big Bang. And so the elements in their standard states have heats of formation equal to 0. That is not true for entropy, right? Like even, pure elements like oxygen have measured degrees of disorder. Like they have possible microstates, especially, right? If you're talking about like at this temperature, they have kinetic energy, that energy can be distributed. And so there's a messiness or a degree of disorder associated with even the elements in their standard states. So these values are not equal to 0 in any case, except third law of thermodynamics tells us the only time where you have a 0 value for entropy is when you have a pure crystalline solid, pure meaning like not mixed with any other substances, and it's at 0 Kelvin. I recognize that looks like okay, but I mean at 0 Kelvin, okay? So the only time it's 0, so you're never gonna have a standard value at 0, right? Because that's not at 0 Kelvin. So when all molecular motion stops at 0 Kelvin, that's the only time that you're gonna have an entropy equal to 0. So remember, just like delta H's, hey, remember how we could get the delta H of a reaction by doing the sum of the heats of formation of the products minus the sum of the, oops, I forgot my delta, heats of formation of the reactants. We can do the same thing for delta S. So if I want to actually calculate what is the change in entropy of my reaction, all I have to do is sum up, remember N is moles, the standard molar entropies of the products minus the sum of the standard molar entropies of the reactants. And we just look those up, like I said, in Appendix C to get the actual numerical entropy change for the reaction. I also think I forgot to talk about units here. The units for entropy are, remember, we're talking about energy here, right? Possible positions and distributions of kinetic energy. So energy, joules, per mole, Kelvin, okay? Because the temperature at which something is at is really going to affect how much disorder it has. So these are our units here for entropy. When we were talking about delta H's would typically be measured in kilojoules, not joules, but kilojoules per mole. So that's our unit here for delta H, and joules per mole Kelvin is our unit for delta S. Now, let's do a practice problem together. So if I want to calculate what is the entropy change for this reaction, numerically speaking, I could first look at it qualitatively. See how I have 4 moles of gas here on the left, and I only have 2 moles of gas here on the right? We would say that this is becoming less disordered. Hit that button again. Less disordered, which in my words is more ordered. And that should be a negative delta S. So we can use that to check ourselves to see if in fact we do get a negative value here. Okay, so in order to get my delta S for my reaction, I'm going to take the sum of my products. So I'm going to go 2 times the delta S of, I guess I really shouldn't call it a delta S. Did I call it a delta S? Whatever. Standard molar entropies of my product, NH3, minus my S naught. Oh, why did I make that look like that? Sorry. Oops, I gotta change my background. Or else it's going to get all messed up when I go to erase. See, I'm learning, you guys. Okay. S naught of my N2 plus 3 times my S naught of my H2. Okay, and then I'm going to go look up these values, like I said, in Appendix C. So my molar entropy for the ammonia is 192.5 joules per mole Kelvin minus my N2, which is 191.5. 191.5. Oh, I'm going to run out of room with all these units. I got to write smaller. Plus 3 times hydrogens, which is 130.6 joules per mole Kelvin. Another thing about standard molar entropies, you guys, these S naught values, these are always going to be positive values. Okay, so if we do this math out, 2 times the 192.5 minus 1 times the 191.5, and adding to that the 3 times the 136, hopefully we get 198.3 joules per Kelvin. Now you can see my moles canceled because, technically, right, you guys, this was moles. This was moles, right? So your moles are going to cancel out, and the delta S naught for your reaction would be this. And oh, look, if we go back up to the top and we look at our qualitative prediction, we do in fact get a negative delta S, which means that this reaction is becoming more ordered. I just realized, you guys, I think I said it earlier. Technically, these should not be deltas. It doesn't matter, right? Because these substances don't have changes in entropy. They just have entropy, Sorry. Get rid of those. It's just a force of habit with the enthalpies. Now, the reaction itself has a change in entropy, but the amount of disorder that these substances have is just a standard value. Okie dokie. Did I want to talk about anything else? I guess not today. So I hope that was helpful, a little bit like how we do it in class. Who knows? If you hate listening to me talk on these, you can just go watch a real Khan Academy video, which is probably, I don't know, I like that guy's voice. Okay, so we covered sections 19.1 through 19.4. If you're curious as to what that was in the textbook. And again, the text goes into some details, especially around entropy involved in phase change and whatnot, that I just don't think that we need to get into. I think this review or overview would be good enough for you guys when you walk into your college chem class. And then in our next lecture, after you guys go off and do some practice problems with this on your own, in our next lecture, we are going to see how does this delta S that we just learned about relate to delta H to figure out whether a reaction is going to be spontaneous or not. And the thing that these two things are going to combine into is something called delta G, which is free energy. And the combination of delta S and delta H into delta G is going to determine whether or not a reaction is spontaneous. I know you can't wait. All right. Good luck with the problems, you guys. And I'll see you during our Zoom session. Bye.